So last week, we went through a few examples, tried to calculate the relations between voltage, currents, and VB, VC, IC, IB, IE, and also we link together with one typical example, and we went through the active mode, and then we change the resistance. Basically, this is a circuit that we change the resistance, and we found it was not in saturation, and we have to do basically if it is not in saturation, we did all right, but otherwise we have to redo it. So this was a typical example that you will see in kind of BJT circuits. Again, I want to emphasize the word or the term saturation is very much different from it is in MOSFETs. Yeah, in MOSFETs, saturation is a mode, the current is flat. The current is not flat, that's the triode mode. But in the BJT, the region the current is flat, it's called active mode. The current is not flat, but it's changing, that's an area called saturation. So even though they both call saturation, but they're referring really to different operating conditions, and that is inherited from the original behavior of these devices, and that's just happened that way. We talk about one idea in BJT is we've been saying that if VBE is larger than 0.7 volts, and it results in either a saturation mode or either in active mode, right? So both modes can be called R mode. So we use this one as a first degree of approximation. So you see a diode, you see like a diode. When it's about 0.7, it actually conducts. But in real life, that 0.7 is not a number written on stone. So it's a number that gives you a very first approximation of the device working per mode. So in real life, the BJT will be working even though the voltage is not approaching 0.7. So this diagram, we don't see this quite often, because this shows the relation between IC and VBE. The ones that you see more often is IC as a function of VCE. With VCE changing, for example, with one given VBE, that's how your current will look like. And in this area, we call it saturation region. And in this area, we call it active region. So this is a diagram that we see quite often. But on this diagram, what I did is I only draw one line with one VBE. If we change VBE, that current will change. So if I'm going to say draw a few lines, another line will look like this. And maybe one more line is going to look like this. And each one of this is responding to like different, this will be 3. So now you can see, when we say VB larger than 0.7 volts, it's going to conduct. It's actually, again, just an approximate number, because in fact, VB changes, current changes. So how do you draw the relation between IC and VBE? Well, if we get some, let's say if we draw just one easy way to get it is we draw a line over here. See, and this one will say, okay, if VB is 0, this is your IC increases, right? So get the cross point at each point, and we'll get a current. And then we translate to this diagram. So, okay, I'm going to now draw IC as a function of VBE. So apparently when B, the current is point. And when VB increases, That diagram. It's complexly dark. So once it's started, the current I is summable. So this is the equation that we use to basically calculate this diagram. Oh, now you just out because it's and this one shows current IC as a function of VCE, but also you get a group of, but this purely drawing IC as a function of VBE. So this helps you to understand that IC as a function of VBE, it changes a little bit. But if we want to get an approximation, this is what we do. Okay, well, let's VBE off VBE, and then that kind of and determine it will be determined by external circuit. That's what really this. That's the real device operation. But since this current IC is not only related to VBE, but also related to VT. So VT is thermal temperature. So by its name, the VT will change as the temperature changes. So it's 25 millivolts. Well, if temperature increase, VT will increase. When VT increase, what happens? For the same IS and VBE, IC is smaller. So that's how we calculate here is, yeah, actually, I just said it wrong. It's when T3, well, actually, I said it right. So increase, your current becomes small. It's like T1 has the highest temperature, T2 is second, and T3 is. This is because as temperature increases, VT increases. So therefore, current will become smaller purely by this equation. So there's nothing special about it. And remember that equation, you'll be able to draw the diagram, the curve change. So this phenomena tells you what happens when and we're going to focus on 25 degrees C and 25 millivolts. But again, as just a caution for you guys, go on with your job where you need to design a circuit, whether it's integrated circuit in IC design or whether you're going to design just like discrete circuit for some purpose, you need to keep in mind that your diode, your transistor, your BJT, that VT is going to change because you don't know what kind of environment it's going to work in, right? In California, we are good, 25 degrees C, but if you go to Boston, what happens? Like minus 15, minus 20 right now. That's totally different. Right? When you go to Arizona in the summer, it goes to 60 degrees C. So your actually changes. But not only just the ambient temperature changes, but also all the circuit and the circuit around it, when you design a system, it creates heat with the losses. And that heat will increase the temperature of the components inside some sort of enclosure or on your PCB. And sometimes, like in the military application, they want you to be able to handle 150 degrees C temperature. So this number of VT is going to increase dramatically and your current actually reduce dramatically. So that's something just to keep in mind. So even though in your book, you got always 25 degrees C, but when you go to actual work, it changed so much. you have to consider that, when you design your circuit, like one of the things that you want is my device still working active mode, right? Because if IC changes, you might actually run out of the active mode, so your total circuit is poor. So that's something you keep in mind. You want to design your circuit has some like a room of like some flexibility, room to change. So if we say in the lab, we want to measure between IC, VCE, and VBE, what you can do is a transistor. And you vary, fix one, you change another, you get a group of curve. And you, like, for example, at one value, maybe not 0.5, maybe this still example. Fix VB at 0.5, and you measure VCE as you measure IC as a function of VCE, you change VCE, and you take all the points. Okay, and then you change another VBE, and you start to measure. And so on, you just measure them. And once you measure them, you connect them, you make this group of curves. And at this point, I want to explain a few things on this curve. One is that you see the actual measurement is not a flat line. It's not a horizontal line. Why? Because the one called early voltage. And you guys saw this in MOSFET. So this is similar to that VA. It's almost the same function. So that is going to make your device current increase as VC increases. So not a constant anymore. But if you extend all the lines to the second quadrant, you will see that they are going to cross at the same point. So that point is called early voltage. So it's called early voltage. And that is an important parameter that we need to make use of later. Another thing I want to do is, even though the circuit shows that dangerous if you do it yourself, like in a laboratory at home. Why? Because the current is very sensitive to those voltages. Remember what we're talking about, VBE is 0.7. It's really around 0.7. If it's below, that's okay, because the circuit is not going to connect so much current. But if you go slightly beyond 0.7, the current is going to increase dramatically. And if you go to 0.9, your circuit is actually probably going into saturation already. And you're going to have a lot of current from base to emitter that you actually might burn the device. So since it's so sensitive, we don't recommend doing this type of by hand. But you can buy an instrument like from TI. They have this. You can plug in your device onto these curves. Also typically, you guys do simulation. You download the data sheet, and you're going to curves that's already given to you, and that is based on measurements done by the company who produce the semiconductor devices, and also that is based on the typical performance. Each individual device with the same part number might change slightly, but the average performance of this one. So now you want to say, okay, so if that current is right? And I'm going to say this triangle here, the small triangle, is going to be similar to the large triangle. So if I know the current over here, and the height of this one, I can get the total current of this one. So by mathematically, we found that IC is equivalent to this one. And this is this just extra term. This extra term. You see, the first term is the equation that we've been using all the time so far. But the second term is due to the VA, which makes the current not flat anymore. So that's where you get that one. So if we turn that equation above, you can say, well, this equation will become IC equal to IS times e to the power VBE divided by VT, and then plus IS VCE over VA. So if you extend the equation, you can say there is also IS times e to the power blah, blah, blah. So, but really, so I can, in fact, I don't have all this. I simply write I can write as a function for this IC plus 1 times ECE VA. And that gives you IC plus IC over VA times. So really, I want to write the IC over VA because later on I can define VA over IC as RO. This is resistance. Because once IC is given in the circuit, VA is related to the device. This one doesn't change, but IC could change. So you actually, if you change your IC, this RO is going to change. But if you fix IC, this RO is fixed. So I have this RO, I plug in back to that equation. What I got is I would have IC equal to IC plus VCE over RO. So this is the equation that this equation represents how much current, how much more current that you get when VC increases. So when VC is very small, like 0.3 volts, and this is negligible, so your total IC is determined by the exponential expression. But when VC increases, this number becomes more dominant, and sometimes can be as much as IC itself. So it depends on how much VC that you have. So this says that when you design your amplifier, so your VC shouldn't be very close to the saturation voltage because otherwise the thermal temperature change might impact your operation. But you also don't want to have too much VCE because too much VCE is going to induce additional term plus IC, and that's going to cause your circuit losses and other things, right? So this diagram and this slide tells you a few things. But if we actually redraw the equivalent circuit, so you guys remember the previous circuit that we draw without RO, right? The reason that we can draw that is because IC equal to IS times e to the power VBE over VT. So that's exactly this. And VBE is let me also draw a symbol for that. So you have N-type, you have between base and emitter, you have a base that's called VB. IC equal to IS times VB. VB. Or the same circuit, you redraw it in this way. You mark them. In this case, we mark it, and this side source controlled by VBE. So that's the current at IC. But this identity is just identical. But now what you're doing is that's without RO. Now, when you have RO, what you're saying is you're adding a term of VCE over RO. Well, VCE over RO is from here to here. Same thing here. So that's VCE. So VCE over RO. Now the bottom is the ground. You will simply the current equal to this current equal to VCE over RO. So that's your current. So very simple, very straightforward, just simple mathematical transfer from one equation to another. You really get your final expression. So now I think what we're going to do is we're going to look at some examples. But before the example, let me introduce you a few more diagrams. When you guys see this later, you're not going to get confused. So this introduces a concept called comma emitter. So comma, this word, you're going to see them often in amplifiers. Comma means together. So, and also sometimes it means ground. So in electronics, when we say comma emitter, what we are saying is emitter is common with ground. That's the full expression. Just say the emitter is grounded. So by the meaning, you can extend. If I say common collector, what does it mean? The collector is grounded. If I say common base, the base is grounded. If I say common source, the source is grounded. However, there's one thing you have to be careful. The comma typically refers to AC in the concept, in the context of this class. So you might say, how can you ground a collector? Well, the collector is not grounded for D. So when you guys in the lab doing the oscilloscope, you remember you have buttons where you say AC, and sometimes you say DC only, or sometimes you say AC only, sometimes you say together. So when you push that button, it measures everything, including DC and AC, but you press AC only, it filters out the DC, but you only display AC. So this is what happens in your future. Like if you have a waveform like this, you have DC and AC. So the DC IC, like didn't do that. Well, remember, there's one important. The very first lecture I went through circuits, we have superpositions. Okay? So when you do superposition, what do? You open the current source, you ground, you short the voltage source. So if you have a voltage source, when you do superposition, what do? Well, you do one AC plus, let's say you got IC, IC, and your total IC, your total I, let's call it something. This total I, typically it's called capital C. So I capital C equal to IC plus lower C. So you do superposition, you do DC separate, and you do AC, you add them together, that's your total current. So what this does is in the future, when you guys do problems, like in this class, biasing with capital IC. But when we move on to chapter 7, we start to talk about small signal, then we forget about the DC biasing. We do a lot of small signal. So we do the lowercase I. So that's a small signal, and that's a DC biasing. Right. So much about the common emitter, things like that. And here saying that, so this diagram, back slide over here. So this diagram you see, no? What? Yeah. So this diagram, when we measure the circuit, we had a VBE as a voltage. So we change VBE, we measure VCE and IC. So we got this group of curves. But you can also do a current source at the base. I mean, so we go back one slide here. So on the left hand, we measure VBE, we apply VBE, we measure IC. But then on the right hand diagram, we inject IB, we can measure IC as well. But of course, that IB and VB, they are related anyway, so it doesn't matter. But the good stuff about this circuit is that you inject a constant current source into the base, so it doesn't really, it's not easy to burn the device because you're injecting a current source instead of voltage. Oh, if your VC is too, you might still have trouble because your current is actually also related to VCE. So when VCE increases, the top graph is the actual like an idea, well, not really idea, but I mean more ideas like device. And then the bottom graph, this one shows a more realistic device, a practical device. So by now, if I would say we would have three types of curves. So one curve like this is saying VA is infinity. VA is infinity, right? So RO is infinity. But in this case, you have this curve here, and VA is a constant. But in this case, it's more. Oh, sorry about that. Okay, so the top one is still like it's not ideal, but it's sort of kind of didn't look at the more details at this area, the saturation area, but it's more like a linearized circuit. But this is a more practical circuit. As you can see, as you increase VCE, if your VB is small, it doesn't change. But when VB increases, this line starts to get slanted more and more. So that's a group of curves. So just like that. And then sometimes if in a saturation mode, so remember when we say in saturation mode, VCE is less than 0.3 volts for saturation, right? So VCE is larger than 0.3, this is going to be active mode. But if it is less than 0.3, we'll typically think it's in saturation mode. But how low can it go in saturation mode? We think typically it won't go too low, but 0.2 is kind of average. So we think that. So we fix VCE saturation to 0.2 volts, but this happens at VBE is large or equal to 0.7. So you put this together. So instead of saying, okay, VB is 0.7 or more, exactly 0.7. So in that case, your device really just becomes sort of two, like this is whole device. So this device equivalent to like this. And if this device in any circuit, you can replace this device with that model, and it will represent your operation. So let's do kind of a sort of example. So if I have a BJT that works like this. So if I have a circuit, just simply like this one, and I already tell you that this is, if I want to do is I can simply replace that with a model of the BJT. And if I say this is, say, 5 volts, and this is also 5 volts, so I would get 5 volts here. Let's say this is 10K. This is 100K. So I will have 5 volts divided by 100K, and this is 10K. So I'm going to write on top here, say how much current we have. So since I replaced this circuit inside the blue is my equivalent circuit, and I have on the left hand, I have IB equal to 5 volts minus 0.2 divided by 100K. So I get 0.048 milliamps. And on the left hand, I have IC equal to 5 minus, 0.7, sorry, 0.7. So this could be, yeah. Let me rewrite this one, make it sure. So it's VB, so 5 volts minus 0.7 is VBE divided by 100K. That gives you 0.043 milliamps. And on the right hand, we have IC equal to 5 volts minus 0.2 divided by 10K. That gives you 0.48 milliamps. Now, this two numbers, if I use these two numbers divided each other, it's still like more than 100, no? 0.043, 4.3, yeah. So this is 0.48, 4. Yeah. So I use this 48 divided by 4.3. So yeah, so it is in saturation because if you look at the beta, it's going to be IC over IB. It's going to be much less than 100, so roughly 10, 15. So that is actually in saturation mode. So use example to illustrate if you know it's in saturation mode, you can use this and IC. Okay, so it just makes your life simpler. But you don't typically need the equivalent circuit. So often this equivalent circuit often helps us to understand in the initial phase. But once we know how they work, I don't see a lot of engineers go to that equivalent circuit model because it really doesn't. You don't need to. You can observe them on the circuit itself. So let's move on with the example. So this one tells you they want us to find VBB in the active mode. So A is in active mode, VC is 5 volts. And you guys can see already the numbers already defined. The VC is here, VB is here, and VBB over there, the resistance given, and IC flows through RC and IB through RB. So the ask us to do the active mode, VC is 5 volts. And the second says at the edge of saturation, really means 0.3 volts at between active and saturation mode. And fully saturation 0.2 volts. And also assume VB is 0.7 and bed is 50. Now, of course, we a different number, but that's what the problem gives. We do all this assumption and we can start to solve the problem. So the first one is active mode. They want to find voltage VBB. Right. So in active mode, means VC was given at 5 volts. So we can calculate, so this is 5 volts, and this is 10 volts, right? So we can see the difference between VCC and the connector has only one resistance, right? So it's easy to calculate the current IC equal to, will be VCC minus VC divided by this RC. Of course, you know that VC is equal to VC because V is grounded. So VCE equal to VC minus VE equal to VC. So VC is 10 volts. VC is 5 volts. Divide by 1K. That gives you 5 milliamps. That's the first step. So that calculation really didn't involve anything about transistor yet, because we know the voltage at the bottom and top of the resistance, therefore we can easily calculate IC. But the next step is that because it's in active mode, here we need to use the equation already. So because in active mode, we know that beta is IC over IB, right? So in this case, we can calculate IB equal to IC over beta. And beta is 50, IC is 5 milli, divided by 50, that gives you 0.1 milliamps. So from IC, we can calculate IB. Now, if IB is 100, apparently this number is going to be different, right? So, but now IB is 50, that was given, so we use a 50. So, like if you go to exam, you forgot to read the question, you simply say, oh, I'm going to divide by 100, you got some number that's going to be wrong because IB was given at 50. It's not 100, even though we said the typical value is 100, but it doesn't not guarantee the device is always 100. So you have to read the problem and make sure you use the right value for beta. Right. So now we found IB, and VBE was assumed also given. So VBE was 0.7 volts. So if you have VBE is 0.7, how do you calculate IB in this case? Well, IB will be VBB minus VBE divided by RB, right? So, and VBB is given, is not given, but IB we calculated already. So therefore, we would be able to find that VBB, we multiply on both sides by RB, we'll find is IB times RB plus VBE, right? So when we find VBB is going to be, IB is 0.1 times RB is 10, so that gives you 1 volt plus VBE equal to, well, VB is 0.7, so it's going to be 1.7 volt. So we simply use the current flowing into the base. We get 1.7 volts to get that. So we solved the very first one we found it. So the next question is find, so find VBE at the age of saturation. So when it says at age of saturation, what it means is that VCE equal to 0.3 volts. So if we see 0.3 volts, now you can simulate exactly the same procedure we did. Is IC is going to be 10 minus 0.3 divided by 1K. That gives you 9.7 milliamps. Because it is at the age, so therefore, this equation still works. So it's going to be 9.7 divided by 50 That gives you how much is it? 0.485 milliamps. So you get IB. So similarly, we can calculate VBB. It's going to be IB times RB plus 0.7. And IB is plus 0.7. How much is that going to give you? 4.85. No, actually, this number is wrong. This is terribly wrong. I was dividing by 2. It was dividing by 50. So that's 9.7 divided by 50. That's 1.6. How much is it? 1.85 or something like that. 1.8, 1.9. Okay, let's put it 1.9, 0.19 milliamps. 0.194. Okay. Oh, what happened? Okay. Okay. Sorry about that. This is sensitive. I somehow cannot control it. All right, so 0.194 milliamps. So here I change it to 0.194 times 1.94 plus 0.7. So that gives you 2.64 volt. Okay. So that's how we can calculate the at edge of saturation, B10. It's still linear mode, but almost go to saturation. So we see 0.3 volts. The next question on this example, it try to look at it's in deep saturation. So remember last lecture we talked about why it is in deep saturation means so IC can all so I and IC, it becomes a definition called B beta worst. So that is IC, let's call it saturated current divided by IB. And that is typically less than beta. So if it's a beta 100, beta force is much less 100. So in this case, the condition that was given was if beta force is 10. So beta force is 10 means IC is equal to beta times IB, or you can say IB is equal to IC beta F. Now, since it's in deep saturation, we know that VCE is 0.2. That was given from the problem. So in deep saturation, VCE is 0.2. So if VCE is 0.2, we can calculate IC going to be 10 volts minus 0.2 divided by 1K. That gives you 9.8 milliamps. So now we can calculate IB, which is IC over beta, which is 9.8 divided by 10. That gives you 0.98 milliamps. We found IB. So similarly, we go on to calculate VBB is IB times RB plus VBE. So VB is still 0.7. So that gives you 10K times 9, so 9.8 plus 0.7 gives you 10.5 volts. So we can probably do a little bit of summary over this corner for the three conditions that we just calculate. For the same BJT, we're able to run it in at age, active and saturation, and we can run the BJT into deep saturation. While we transition between the three different modes, what we did was we kept VCC. So those are the same thing. The only thing we changed VBB. So when VBB is small, you're in active mode. When VBB increases, you move from active to the edge of saturation. And you increase VBB more, you're moving out of active, you are going into deep saturation. So that's the three different modes because VBB has changed. So over here, I want to ask you guys, if I fix VBB, what things can you change to make this BJT working in three different modes? So that's the first one. We want VBB increase, it goes from active to saturation mode. So I want to ask you, what is the second method? If I keep VBB untouched, you change, or which one are you able, one of them, you can change to still move the things to go from active to saturation. So you fix VBB at some value, it doesn't matter. You can fix at whatever value, like 2.64, for example. What can you change to make it to go from saturation to active to saturation, or from saturation to active? What one thing you can change? So you guys not sure, look at this. What that says is that the relation between IC and IB, if that ratio is too small, it goes into saturation. If that number is equal to beta, it is in active mode, right? So in order to make this one from active to saturation, all you need to do, you can do one of the two. You decrease IC, right? So you decrease IC, but it reduces. You fix IB, but you fix IC. Or, but you increase IB. So what we did was, by changing IB, by raising VBB, we're increasing IB in the circuit. That's what we done before. So now I'm saying fix VBB. But in fixed VBB, if I want to increase IB, what do I do? Over here, fixed VBB, you want to increase IB, what can you do? Reduce IB, RB, right? So if RB decreases, and it goes from active to saturation mode. That's the second one. And the third one, of course, is that what else? If I fix VBB and I fix RB, what else can you change? There's only one thing left. RC. What do you do with RC? You can move from active to saturation. Basically, you're reducing IC to move from active to saturation, right? Reduce IC means you increase RC. So when RC increases, and it goes from active to saturation. You see, for the same transistor, in the VBB, or there's actually one more, is you can change VCC too. So if you reduce VCC, what happens? If you reduce VCC, same thing. IC decreases, beta decreases, you move from active to saturation. So we really have 4 different ways to change the operating mode of a BJT. And so this is this example. Any question on this example? No? So it's fairly simple with a single device. And so moving beyond this point is more all like examples. So apparently we might do like 1 or 2 examples today, and we're going to do more next week, and then a lot more in the following lecture. So here is the equivalent circuit that we have seen many times. The top one is the active mode, and the bottom one is the saturation mode. And we just saw this one a few minutes ago, where we use this voltage source and this voltage source to represent the PN junction here, forward, and the PN junction reverse biased. So we have VBE 0.7 and VCE saturation at 0.2. So that's the saturation mode. The top one is the active mode. On the right hand, we have we're flipping E and C. So the emitter is up and the collector is down. So current is splitting from emitter to base and to collector, and the current coming out of base instead of going here, will go into the base. Right? These are the equivalent circuit that you will do quite a bit. Okay, so we're going to do another example, kind of go over the different operating conditions. In this case, given like the resistance, find out all the voltages and the currents in each branch. The only thing we don't know whether it's in saturation or active mode. That's we don't know. So since we don't know it, we have to start with an assumption. We're going to assume in one mode, and we calculate it, and we go back to verify. If the results shows that our assumption is right, you're done. If result shows that your assumption is not correct, you have to go back to do it in another mode. So let's, it's nothing wrong to assume in one mode or another, but just, you have to start with one. You might be lucky that you made it the right assumption, you're done, but maybe not so lucky that you have to redo it by doing another assumption. Okay. So in this case, what I'm going to start with is I'm going to assume in active mode. Okay. So I'm going to assume it's in active mode. So therefore, I also assume VBE is 0.7. Okay, so I didn't talk about this thing going to be in like a cutoff mode. It's not going to be a cutoff, right? Because there's voltage at the base at 4 volt. If it is in cutoff, what happens with currents? Cutoff means no current. If there's no current, what is the voltage at VE? If no current, 0, right? Because no current, there's 0 voltage of 0. So from base to emitter, it's going to be 4 volts. So that's not possible. So therefore, it has to be in conduction mode. So that's why I didn't talk about it. So we assume will be 0.7. So by doing that, our second step will be find IB. The reason is from here to here we have a loop. So that loop says 4 minus 0.7 divided by 3.3 will give you the current. So 3.3 by 3. Then we have 1 milliamps. And 4 volt minus 0.7 is a drop, and I got that 1 milliamps. So if I have that 1 milliamps, The next step I can do is I can find VE. VE will be no, actually, I did it wrong. Sorry. No, actually, it is right, but I did IB wrong. This is going to be, so the current that I calculate is not IB. What is it? The current I just calculated, which current is it? It's IE, yeah, it's IE, it's not IB. It's IE. So now we say VE is 4 minus 0.7, it's 3.3 volts. Okay, so the next step we can do, of course, 2 and 3 can be flipped, it doesn't matter. So I'm going to calculate VC. So VC is VCC minus IC times RC, which is equal to 10 volts minus, oh, actually, I'm too early. So I cannot calculate VC yet because I need to calculate IC. I want to calculate IC because if I know IE, so IC is alpha times IE, because beta is 100, so alpha is 0.99. So it's going to be 0.99 milliamps. So now I can calculate VC because see, I need to go IE to IC, or VC is VCC minus voltage drop RC. So I'm going to plug in the numbers, see what we get. So it's going to be 10 minus 0.99 times RC is 4.7. So this is going to be, anybody has a calculator? I'm going to get some numbers because we want to determine whether it's in saturation or active mode. If we don't have the number, we cannot go back to verify. So it's going to be 0. Almost like a 5 volts, right? 5.347. Okay, that's good. 3.5 volts. So our VE is 3.3. So now we're going to do VCE. So VC is VC minus VE. It's going to be 5.35 minus this VCE is larger than, so it is in active mode. To do the first step to find VCE, because we have to make sure VCE is more than 0.3. If your VCE is less than 0.3, sometimes it's a negative number, which means you did it wrong. VCE cannot be negative. Therefore, you have to go back to assume it's in saturation and do everything again. Of course, the process is going to be slightly different. So let's look at the actual solution. Give it to you here. Now, before go to the next example, in fact, I want to do just like a few like more discussions here. So if I, like here, apparently we're done. It is in saturation. But let's say here, I want to adjust the 4 parameters we can actually change. Voltage here, resistance here, voltage here, and resistance there. If I change some of the numbers, I want to bring this transistor into saturation mode. How to bring it into saturation mode? I mean, this is purely exercise. Why do you want it in saturation? Well, This is purely exercise. How there's 4 parameters we can change. We want to make it in saturation mode. What can you do? What are the, like, what is the trend? We can do from the previous example, similarly. So what do we do if we increase VBB? Let's go VBB, VCC, okay? If we increase VBB, what happens? If you increase VBB, IB increases, right? So for IB increases, your beta is IC over IB will decrease. Now, if the IB increase so much that your beta now is less than that ID 100, you're in saturation mode. So that's one thing you can do. What else can you do? Instead of, yeah. If we decrease VCC, what happens? IC decrease. If IC decrease, beta decrease. If beta decrease to the point that it is less than 100, it's in saturation. Okay, what else can you do? Yeah, increase RC. Same thing, increase IC, IC decrease, okay? And number 4. Is decrease RE. If you decrease RE, you decrease RE, it makes IE increase. If IE increase, IC doesn't change, IB increase, so therefore your thing will change. So now you have these 4 different ways of making this in saturation. Now I want to make one case. We want to do the saturation mode. So what I'm going to do is I'm going to really do a very bad example. I'm going to do VCC equal to 5 volts. Maybe I change VCC. 5 might not make it in saturation. So I'm going to make it really small. I'm going to make it into 4 volts. I think this will probably make it in saturation. Let's try. I didn't do this yet, so we can do it together. So if VCC is 10 volts, what I'm going to do, I'm going to assume it's in saturation because this is what I wanted. So if I want to make it saturation, I have VCE 0.2 volts. If I have VCE 0.2, I'm going to calculate IC, but IB didn't change. I mean, IE didn't change, right? So IE was the same because IE is still going to be 4 volts minus 0.7 divided by 3.3. That gives you 1 milliamps. So now I'm going to calculate IC equal to, because I assume it's in saturation, right? So, okay, before I calculate IC, I have to calculate VE. So, but VE is just already. Of course, V is 0. V is 4 minus 0.7 is 3.3 volts. So VE is 3.3. That's given. And here is VCE. So I will have my IC equal to 4 volts minus 0.2 minus 3.3 divided by RC. RC didn't change. So that gives me 0.5 volts divided by 4.7K. That gives me 0.1 milliamps. Wow, 0.1 milliamps. So that really does the work. So here we're going to get beta equal to IC over IB equal to 0.1 divided by 1. That gives you 0.1. So beta is so small, it's only 0.1. So absolutely it's going to be in saturation. Because I did it, I wanted to make sure it is in saturation. So I did 4 volts. It's probably going to go, if you do observation, you probably can do like, this is 3.3. So if this 3.3 plus 0.2, that's 3.5 on top of there. So 3.5, anything that plus 4.7. So yeah, so this thing is easy to be in saturation mode. You don't need 4 volts. You probably 1 to 6 or 7 volts, it will be in saturation mode. Now, of course, that example, I had time. Let me see. Yeah. So let's do one more example. We're going to finish. So this is the same example. But what it did is it was trying to say, instead of 4 volts, it changed to 6 volts, VBB. The example that we did was 4 volts, and then we changed VCC to 4 volts. But here, VCC is the same. We changed VBB to 6 volts. That's the only thing changed. So if this thing changed, your IB will change. So your IB will become 6 minus 0.7 divided by 3.3. That gives you 1.6 milliamps. If you go to 1.6 milliamps, you want to say, okay, if it's in active mode, so this means assume. Again, we don't know. So assuming active, you get IC equal to IE over alpha. You get 1.5, like 8 milliamps. And you calculate VC equal to 10 minus IC over times RC. That gives you what? 10 minus 1.58 times 4.7. That gives you almost like 2.5 volts. But your VE is 3.3 volts. You see? The linear mode, your 2.5, but your VE is 3.3. That's not possible. VC cannot be less than VE. See? VC has to be higher than VE, at least 0.2 if it is in saturation. If it's in active mode, it will be much larger than 3.3, right? So that's why this assumption is wrong. It's impossible. So we say, no, this is wrong. We have to go back to assume it's in saturation mode. So if it's a saturation mode, IB didn't change. So IB will still be 1.58 milliamps, but IC now have changed. So IC becomes 10 minus 0.2 minus 3.3 divided by 4.7. And then that gives you 0.9 actually 5.3. No, hold on, give me. This is a 5. Yeah, no, this is the not 3.3. This is 5.3. Sorry, the number here. This is 5.3. I was using 4 again, so it's a 6 volt minus 0.7. Okay, so 5.3. So this is 5.3 means here is 5.3. So 10 minus 5.5, 4.5 divided by 4.7, it's almost 1 milliamps. So now you calculate your beta is IC over IB, which is 0.96 divided by 1.5, 1.6, let's say 1.6. So this is less than 1. You see what happens? It is small. Your beta is less than 100, and your VC to be, so this is good. So now I said, this is wrong, this is okay, right? So I think I'm going to stop here, unless you guys have questions, but otherwise I'll see you on Tuesday next week. Since you guys are here, I want to remind you, do the lockdown browser practice, download the browser before just you don't get scrambled, to find, oh, how long good it. You can do as many times as you want for the practice, okay?